Welcome back to all. So this is the 14th lecture on quantum mechanics, and in this lecture I will talk about particle in a three-dimensional box system. So in my earlier lecture I have give a brief introduction about a system that is called particle inside a one-dimensional box, and in that lecture I have derived the Schrodinger's equation for that system, that is called particle inside a one-dimensional box system, where the particle reside in a one-dimensional box. Inside that box the potential energy of that particle is zero, and there is an infinite potential barrier of that inside this box, so the particle cannot go outside this box. So there is zero probability of finding that particle outside that box. And also we have derived the expression of wave function for that particle inside a one-dimensional box, as well as the expression of energy for that particle. Now I am going to three-dimensional. So same type of system, that is in the particle, instead of confining inside a one-dimensional box, now it is confined in a three-dimensional box. So you can see that this is a three-dimensional box. These are the coordinate axes along x, y and z, and this is the box, and inside this box the particle reside. So similar to particle in a one-dimensional box system, there is a infinite potential barrier outside this box, so the particle cannot go outside this box. So within this box there is 100% probability that the particle can be find out, and these are the length of that box, Lx, Ly, Lz, along three separate direction. So this is the modified Schrodinger's equation for particle inside a three-dimensional box. Here you can see that instead of using second derivative with respect to psi x, we have to do the partial derivative with second partial derivative with respect to x, y, z, as this box is three-dimensional box along these three axes x, y, z. So we have to take the second partial derivative along three directions. So the Hamiltonian will work on three separate directions, x, y and z, and as the potential energy inside this box will be zero, so that's why the potential energy term will not be there, only the kinetic energy of term, that is the kinetic energy operator, will be there. Now this term is a very big term, so each time when we will going to write the Schrodinger's equation for a particle in a three-dimensional box system, it will take so many space and time to write this big equation. So for our own convenience, we have replaced this whole term into a shorthand operator, delta square, that is called delta square or Laplacian operator. So by writing in this way we can save lot of time as well as efforts. So similar to particle inside a one-dimensional box, for a particle in a three-dimensional box also has some boundary condition, and the boundary condition is as follows. Now the wave function for psi is equal to x value 0 as well as psi is equal to x value Lx will be 0, as there is zero probability of finding the particle outside this box. So that's why at the edge of the box along each direction the wave function will also be 0. So at the edge for x is equal to 0 as well as at the edge for x is equal to Lx, psi value will be 0 for all value of y and z. Similarly, situation occur where at the edge along y and z direction the value of psi will also be 0. So these are the three boundary conditions that is valid in case of particle inside a three-dimensional box. Now we can apply the separation of variable to write the equation psi, which is a function of x, y, z, into three separate wave function along x, y and z direction. So you can see that psi, that is a function of x, yz basically a product of three wave function, and each of them are wave function of one dimensional system along x, y and z direction. Now when we do these types of separation of variable, we will get that the total energy will be actually sum of energies of each direction x, y, z. So the total energy will be Ex, Ey, Ez, where Ex is the energy along x direction, Ey is the energy along y direction, and Ez is the energy along z direction. So this process is called separation of variable. So our equation separate out into three separate Schrodinger's equation, one for each dimension. You can see that this equation is for x direction. So the solution of the wave function along x direction will be this one. Similarly, the wave function and equation along y and z direction will be these. Now, as we have discussed that to do the normalization for any system, as we know that the particles always remain inside that box, so there is 100% probability of finding that particle inside this three-dimensional box. So if we do integration along three direction like 0 to Lx, 0 to Ly, 0 to Lz, if we integrate this wave function, then we will get the value 1. So this is the normalization condition for a particle inside a three-dimensional box. If you remember my other previous lecture, we have done similar kinds of normalization condition for a particle inside a one-dimensional box. In that case, as there is only one dimension is there, so instead of three integration, we have to take only one integration in that case. But here, as there are three dimensions are there, x, y, z, so we have to take the integration along three separate direction, 0 to Lx, 0 to Ly and 0 to Lz, and this is called probability density function. So the integration of this probability density function, which is psi star into psi, will be 1. That is according to the normalization condition that we have imposed. Now by using this normalization condition, we will get the normalization constant, that is total normalization constant, and the total normalization constant will be the product of the normalization constant along each direction, that is Ax, Ay and Az. And we know that the normalization constant along x direction is root 2 by Lx, similarly at y direction root 2 by Ly, and z direction root 2 by Lz. So the total normalization constant will be the product of these three separate normalization constant, that is equal to root 8 A by Lx, Ly, Lz. So if we write this wave function psi, which is a function of x, y, z, for a which is a wave function for a particle inside a 3D box, into three separate wave function along x, y, z direction, then we can express this wave function like this. So we know that the wave function along x direction is we know the equation for a wave function along x direction, y direction and z direction. So we will get the total wave function by simply multiplying these three wave function, and the equation of total wave function will be like this. So similarly, the energy expression will also be similarly sum of along three dimension x, y and z. So that's why the energy expression for three-dimensional system for a particle inside a box will be like this: nx square by lx square plus ny square ly square plus nz square by lz square, or minus h cross square by 2m will be a common factor, so that's why it will be come outside this third bracket. So this is the energy expression for a particle inside a three-dimensional box, and this is the expression of wave function for a particle inside a three-dimensional box system. Now I will talk about degeneracy in a particle in a three-dimensional box. So it is very important to know what is called degeneracy. So basically, degeneracy is existence or occurrence of more than one energy levels having same amount of energy. So if more than one energy levels have same amount of energy, then the phenomenon is called degeneracy. Now we will see that how in a particle in a three-dimensional box this degeneracy occurred. Now this is the energy expression for a particle inside a three-dimensional box where nx, ny, nz are quantum number along x, y and z direction, and lx, ly, lz is the length of that box along x, y and z direction. Now if lx, ly, lz these are not equal to each other, then each level has different energy. But suppose that the box instead of this the box is a cubic box, so the length of that box along x direction, y direction and z direction becomes same, that is lx, ly, lz is equal to L for a cubic system. Then what happen, this term will be a common factor, so it will come outside this third bracket. So the modified equation for a cubic system will be E nx, ny, lz is equal to minus h cross square 2m into nx square plus ny square plus nz square is equal to L square. So this is the modified energy equation for a particle inside a 3D box, but this box is a cube. Now what happened for a energy level 211? So this is the quantum number. Now you can see that for a 211 you have to put nx value 2, so it will be 2 square plus 1 square plus 1 square, so the total energy will be minus h cross square 2ml square into 6. So this is for 211. So same value of energy also we get obtain for E is equal to 121 and E is equal to 112. We get the same energy, that is called h cross square by 2ml square into 6. So you can see that for cubic system these three energy levels are degenerate, or they have the same energy if the system is cubic. But if the system is not cubic, if Lx and Ly and Lz are different, then this value E211 will not be equal to E121 or E112. So you can see that the occurrence of degeneracy is due to the symmetry in the system. So as the symmetry is in the system is there, so that's why Lx is equal to Ly is equal to Lz. So that's why this degeneracy occurred. So it is very important statement that if in any system degeneracy occur, it can be due to the presence of symmetry in that system. So if you see that if Lx is equal to Ly not is equal to Lz, then we would have less degeneracy. So more and more symmetry in the system increases, we will see more and more degeneracy in that system. Now here I have plotted minus h cross square 2ml square term, and you can see this is the energy expression for a particle inside a three-dimensional system. Now we will see that how many degeneracy will be there for which quantum number. Now you can see that this term is fixed, minus h cross square 2ml square. Only this term will change for a cubic system, nx square plus ny square plus nz square. Now for a energy level E111, there will be only single energy level which has energy minus 3h cross square by 2ml square, or you can see 3 is the common term, 3 is the main term and this term is the common one. So this is the value will be 3, the factor will be 3. Now for a 211 energy level, it has 3 degenerate energy level, because 211 can be 211, or it can be 121, or it can be 112. So each has same energy value, so that's why it is triply degenerate system, and it has energy of 6h cross square into 2ml square. Similarly for a energy level of 221, it has 3 degenerate energy levels, and these 3 degenerate levels has the energy E221, E212, or it can be E122. So all these 3 energy levels are having same energy, that is minus 9h cross square by 2 ml square. So it is also triply degenerate. Similarly, you can see that the energy level of E222 it can be expressed by only one way. So that's why it is single system. It has no degeneracy in that system. On the other hand, the system that is called energy level 1, 2, 3, and this 1, 2, 3 can be written in 6 combinations. So that's why it has 6 degenerate energy levels, and each energy levels having energy 14 h cross square by 2 ml square. So you can see that due to the presence of cubic symmetry in the system, we can obtain so many degenerate energy levels. Like in case of 211 and 221 system, we can have triply degenerate system, and in 1, 2, 3 energy levels we can have 6 degenerate system. So up to this, if you do have any questions regarding this lecture, you can ask me through the comment section. I will be very happy to answer all of your questions through the comment section, and please do subscribe to my channel and take care of yourselves. And in the next lecture, I will talk about very important topic of quantum mechanics, that is postulates of quantum mechanics. So stay tuned for my next lecture and take care yourself. Bye.